All right, so today we're going to talk about 8.3 torque. We're going out of order a little bit. We're going to skip 8.2 for now and come back to it after we have finished 8.3. So torque is going to look at force. So we've talked about angular velocity, we've talked about angular acceleration. And so now we're just going to kind of continue with those things that we've talked about in the linear aspect. We're going to again talk about them rotationally. So a force can cause rotation, and the effectiveness of this force, or how much force we have to apply, depends on where we apply it and in what direction we apply it. So, for example, if you look at this revolving door, or if you think about tightening a nut with a wrench, all right, the nut, you have to apply much less force when the wrench is farther away, when you're applying that force farther down the handle of the wrench, than if you were to try and apply it closer to the nut. And again, less force is needed to push this revolving door if I go to the outside of the revolving door as compared to closer to the handle or closer to the axis of rotation. So that's what you need to get from that. The further you are from the axis of rotation, the less force you have to apply to cause that rotation. Let's move this up here. All right, so our definition or our formula for torque is given here. Torque is equal to the radius or the distance from the axis of rotation. That's what we mean by radius, times the force that we apply, and that's known as torque. So it's a product of force times distance, very much like force linear is mass times, is very similar to that. Work is force times distance linearly. Torque is the product of the force that you apply times the radius or the distance from the axis of rotation. Has the same units as force or as work, newtons times meters. All right, so here's an example problem. To open the door in figure 813, that's that revolving door that we just looked at, the tangential force is applied at a distance r from the axis of rotation. The minimal torque required to open the door is 3.1 newtons per meter. What force do you have to apply when you're at the end or further from the axis of rotation or closer to the axis of rotation? So it's just a plug and chug type situation. So we go 3.1 for is our torque. So our force is going to be equal to torque divided by the radius. All right, so we're going to just plug into the formula. So 3.1 divided by the radius of 0.94. And that gives us 3.3 newtons, if I'm not mistaken. 3.1 divided by 0.94. Yes. Okay, and then we'll do the same thing here. So again, 3.1 is our torque. We're going to divide that by 0.35. And so obviously we're dividing by a smaller number, which means our force is going to be a larger number compared to A. So those are just pretty much plug and chug, pretty simple. Please make sure you remember that our equation is torque, and that's our Greek letter there, times the force times the radius. Okay. All right. All right, so you can look at these two figures here below. We have the one on the left. Okay, this shows that a force acting in a direction that is directly toward or away from the axis of rotation causes no rotation. So if we're applying a force here, it's applying this force directly on the axis of rotation, then that does not cause any torque. Okay, that doesn't cause any rotation. But over here, So if this guy is just pulling on the handle for the merry-go-round, then the merry-go-round's not going to go anywhere. It's just there's no rotation there. But if he applies that force at an angle, like you see over here, then that is going to cause rotation. And the force, if it's at an angle relative to the axis of rotation or the radial line, then only the part of that force that is tangential will produce torque. So only this part of the force is going to produce the torque that causes the rotation. So he may apply a force in this direction, but only that component of that force is going to cause any rotation. Okay, so so that means then that for a force that's applied at an angle and not applied, force that's applied at an angle, that torque is going to be equal to the radius times the force times the sine of theta. And this is for a non-tangential force. Okay, so we're looking in this diagram, we're looking at how torque can be defined in terms of a quantity known as a moment arm. So we're going to talk about moments of inertia in the next chapter. So that's where we're kind of getting into this term. The moment arm is the perpendicular distance between the axis of rotation and the line of the force. Okay, so here's the line of the force. Here is the axis of rotation. So this is our moment arm. Okay, so in this figure, the length of the moment arm that you see right here is going to be equal to r sine of theta. And so if we plug that into the equation we just put in, then that means that our torque is just going to be equal to our moment arm times our force. Okay, because we already have r sine of theta right here, and our moment arm, that r perpendicular, that's what that little perpendicular sign there means, that is r sine of theta. That is the same thing. So the moment arm times the force equals our torque. The sign associated with torque is determined by the direction in which it rotates. So if a torque causes a counterclockwise rotation, then that's said to be a positive torque. If it causes a clockwise rotation, then that's said to be a negative torque. So you just want to watch for those terms in your problems, and that will help you determine if your answer should have a positive sign or a negative sign. So if it's counterclockwise rotation, that's going to be a positive sign for torque. If it's clockwise rotation, that's going to be a negative sign for torque. Okay, and if you have more than one torque, just like in linear respects, we just add the torques together. Just like if we have more than one force that gets applied, we add those forces together. So this illustrates a system with more than one torque. So the net torque acting on the system is going to be the sum of the individual torques taking into account their appropriate sign. So remember, one could have a positive sign, one could have a negative sign, because this guy's pulling in, looks like this guy's pulling in a clockwise direction, and this guy's pulling in a counterclockwise rotation. So he would be a positive torque and he would be a negative torque. So your net torque is going to be equal to the sum of those two things, taking into account their signs. Okay, so here is the formula for that. So the sum of all the torques is equal to the moment of inertia times the angular acceleration. So if we didn't want to just add all the torques up together, we could use this formula. We can draw, just like in linear quantities, you can replace the force with torque and the linear acceleration with angular acceleration, and we can obtain the rotational version of Newton's second law. Remember, Newton's second law is equal to force equals mass times acceleration. Well, we're just going to replace those linear terms with rotational terms. So force would be torque, moment of inertia would be mass, which remember mass is just a measure of inertia, and angular acceleration gets replaced with linear acceleration gets replaced with angular acceleration. Same units as before. So the sum of all the torques is going to be equal to the moment of inertia times the angular acceleration. Okay, just like in linear respects, we had quantities that could be conserved, like momentum and energy. We can have the same types of things conserved in rotational motion. So angular momentum is another quantity that is always conserved. So the angular momentum is conserved, just like when the net force is equal to 0, momentum is conserved. The same thing when the net torque is equal to 0, angular momentum is conserved. So the motion of an ice skater can be used to illustrate this. And this is kind of neat coming up because we've got the Winter Olympics coming up in a few weeks. So if you watch those ice skaters, when the skater pulls her arms in or his arms in, that reduces their moment of inertia, their momentum due to inertia. So to counteract that, their angular momentum has to stay the same. So what happens is her angular speed increases. So her momentum stays the same, but she has a smaller moment of inertia. So to make sure that stays constant, her angular speed has to increase, and you'll see her spin faster just by pulling her arms in. Okay, and we have a diagram of that on the next slide. Okay, so in general, if you have a large moment of inertia, you will have a small angular acceleration. And a small angular acceleration that gives the same momentum, angular momentum, as having a small moment of inertia and a large angular speed. Okay, so if she has her arms out like this, let's see, that's her arms. That gives her a large moment of inertia, but a smaller angular speed. So when she pulls those arms in, she now has a smaller I, which means that her angular speed or her rotation is going to increase. And I believe that's it. That is it for 8.3.